full instructor. Yeah. So let's, we should get started with our panel. This is one of the nice features that we have in the summer school. We invited 4 very prominent researchers. In fact, there's probably, it's very unlikely that we're able to have these 4 people in the same room on any given day, given their travel schedule. So we're very lucky today. So I'd like to introduce them a little bit. Yang Xu is from Microsoft, and she's a program manager of their science education program, among others. In fact, she also managed the program that has to do with compiler infrastructure, the Phoenix program. And, so she and I have worked together for years. And she's going to talk a little bit about what Microsoft sees happening in a lot of universities, because she actually physically visits these universities and look at their programs. And Klaus Shelton, he's a world-famous physicist, and his group produced the NAND software and DND, and probably some of you have used the software. And so you're seeing Klaus in person today. This is your lucky day. So the Klaus group and my group have been collaborating on a lot of the algorithm implementations, and his group has contributed a lot to the course itself. So we're very lucky to have him today. And Pratap Venkat is a professor in mechanical engineering. He's one of the best in flow kind of computation. And he and I have been collaborating on some of the implementations of the computational fully dynamic computation. And so we would like to have his opinion on how some of these things will affect the field of mechanical engineering in the future. And Robert Brunner is a professor in astronomy, and he's one of the leading experts in speeding up some of the astronomy calculations we use. And he and I also have been collaborating on quite a few other projects. So all these people are very famous in their field, and they have insight into how some of these computational capabilities can accelerate the research. So what I'd like to do is to have each of them to give a 5-minute opening statement, and just kind of for them to give you some insight. And then I'll open the floor to all of you for questions and discussions, and questions that you're afraid to ask, or questions that you're not afraid to ask. So think about all the questions that you would want to ask. We're going to cut off the panel at 5, but most of the panelists will be around a lot longer, so you can also come with your personal questions that you're afraid to ask in front of so many other people. So yeah, why don't we start with you?
Sure. It's my pleasure to be here. Thank you for inviting me. This is really exciting. I remember last time we had a workshop together in some compiler at UVA. It was on one of the core computing areas. And that's what we do actually at Microsoft, mostly. But recent years, we come to work and made a lot of connections with people in other areas, astrophysics and biophysics and biology and healthcare. And working with scientists really opened our eyes because they bring real-world computational challenges into our picture. And rather than always spending all our time focusing on compilers, working with the new chips, we realize that there are other things that in the real world that computing can really make a difference. At the same time, we also notice a lot of, I personally think it's a serious problem. So I'll give you an example. I think by now you're all familiar with MRI and how computing works with MRI. I was once on the campus visiting an MRI lab, and I was talking to a student. So one of the students, she showed me her program. She just picked up a C book from the bookstore and learned programming herself, and she programmed all these thousands of lines of things and processed her MRI data. One segment I look at it is like a for loop, about 1,000 times. And for these 1,000 times, the program actually do the same kind of convoluted calculations 1,000 times. So if you were trained in computer science, you may do it differently. You may compute and build out a lookup table. So the second time, you do not compute all the things. You make use of what you already do. But she didn't have the training of lookup table kind of things. So I said, perhaps you want to talk to somebody from computer science, get some consultant. We can change your performance from 5 minutes to 5 seconds. By the way, I noticed that the whole program runs for 5 minutes. She looked at me and she said, actually 5 minutes is okay with me. I usually take coffee break. So then later on, I was on the same campus talking to clinicians in the university hospital. And then the doctor there told me, yeah, this is the thing that really concerns me. Because 5 minutes and 5 seconds makes a life-size difference. We don't want to train our students this way. Maybe it's okay in the research lab, but we want them to be ready for the real-world challenges. So therefore, today's research really requires young scientists, to be educated differently. So there's a huge gap between how we do research, taking advantage of computing technology, and how we train students. And you're lucky today here, actually. These are the opportunities to get trained and really pick up the true power of computing so that you would do better and advance the science in a different way. So these are examples I learned. It really opens my eyes, I think. That's all I can say.
Okay. So Wenwei gave me a nice introduction. Particularly, he mentioned the programs NAND and VND that my group is distributing. We have actually many users, like altogether way over 100,000 users. And I understand that about 1/3 of the computer time at major public computer centers is actually used for running simulations with our programs. And so we definitely have a great need to use every trick under the sun to accelerate the computations because they are so widespread and so much used in medicine and in the life science research. I'm actually just a front person for actually people like you who are, if I look here at the faces, I just see the same kind of faces I see when I look at the developers of the programs in NAND and VND who began to use graphics programming units, processing units for computing in our field. We were very fortunate. Last year, for example, 8 of the people in my group took the classes for students and for staff members that Wenwei Wu and others gave here on the campus. It all started, I think, about 1.5 years ago when, again, people of your age took the classes and got really excited about the opportunities there. So I can just tell you from that experience that there is a great chance and there's also a lot of fun. And that's what I like to press, I think, two things. One is that the program GPUs requires really a lot of rethinking. And you may first think, oh my God, that's terrible, but that's really also a lot of intellectual excitement. If you look at our papers that we wrote on the field, on the subject, then you will see a lot of mathematical equations, a lot of strategy speaking. And I think it's much more fun that if you have to really use your brain than if you just, transform code from one platform by deforming it more or less to another one. The opportunities are vast. So it really begins with just hardly getting a factor 1.5 out of speed up to getting a factor of over 100. That depends on, it depends maybe first on the problem. Some problems are just easier to bring to this platform. Other problems require more thinking. They're also then easy to bring, like we have on this campus, in my group, but also at other groups. In quantum chemistry, factors of way over 100 of speed ups. We have in my own group, in molecular modeling, also a speed up of 100 for some problem. For the main problem of molecular dynamics, which is where most of the general molecular dynamics, where most of the applications are, we have sort of factors between 4 and 7. But I can just report to you now that just the latest chip that we got our hands on from NVIDIA gave us a factor 10 now in speed up. So the technology is moving. And our brain is adapting the problem, and so there's really a nice, interesting moving target. Now, the nice thing about these platforms is that even though we have different vendors, there's a lot of intellectual commonality. I think, for example, CUDA is a very good starting point, a generic starting point, to not only work on the process of one company, but also to bring solutions to the process of other companies we know about. So I think we see really fresh wind blowing into our direction, and I think the fresh wind is not blowing against us, but it's blowing in our back and makes us go much faster and having a lot of enjoyment.
So I'll start with Klaus's word, wind blowing in the back. Okay, that's fluid dynamics. so how many of you here are mechanical, aerospace, chemical, etc. engineers? Okay, so you probably have a background of what fluid mechanics is about. So if you want to know what fluid mechanics is, go to Chicago, stand near CS Tower, and see if you can stand the wind. Okay, so that's the recirculating turbulent flow over a building. Okay, and or if you want to be challenging, go to Niagara Falls and see if you can come down in a barrel or something like that. That's the turbulence. Okay, don't do that before this workshop is done. Just like molecular dynamics, fluid dynamics is a very complex subject. Turbulence is probably the most challenging scientific problem that exists. People have given up trying to understand that. So what we do is we basically simulate turbulence. And what that means is we take the Gaussian equations, which are nonlinear partial differential equations, a set of coupled partial differential equations, which we call them the Navier-Stokes equations. Navier and Stokes, these two people who wrote down the mathematical form. And then we use finite volume or finite difference or some kind of a discretization procedure and break down the partial differential equations into a set of nonlinear simultaneous equations. And then you brute force integrate them. Okay? So if you are in the turbulent flow regime, and just to give you an idea, typical turbulence Reynolds number. I think most of you probably don't know what is the Reynolds number, but it's one non-dimensional number. The higher the Reynolds number is, the more nonlinear the problem is. And turbulence starts at some critical Reynolds number, and then if you keep going up in Reynolds number, your spatial scales of fluctuations in turbulence increase. The computer time goes as Reynolds number to the power of 9/4, and that's the number of variables, and the time goes in IQ. So the Reynolds number to the power Q. I'll just give you an example. If you take a simple pipe, okay, typically the Reynolds number that you get in your house, or the flow rate you use, would be something like 10 to the power 5. Okay. To simulate a Reynolds number of something like 5,000, it would take, on my PC, for example, I could do that in about a week. If you double the Reynolds number, you go by a factor of 8. And if you keep doing that up to 10 to the power 5 or 10 to the power 4, you just cannot do it on even the current big machines, parallel machines that you have. And if you want to go to industrial side, this is a simple problem, but if you want to simulate turbulence and combustion in a gas turbine combustor, using what is called direct numerical simulation, it will take forever. Okay, people have simulated a problem with 32 million grid points, and it took about, I think, a year on some big 1024 processor machine. We have a Center for Rocket Science here at the CSE. They take a year of computer time on a 1024 processor to simulate the rocket takeoff. Okay, so you need really a lot of computing power. And that's where the graphics machines come in. I think my student and I are just learning this. We're just only a semester into this. Hopefully with Professor Hull's expertise, we'll be able to speed up the calculations. That's where we come.
As when they kind of introduced me earlier, I've been working with him and others here at SCSA for a while now. You might wonder why an astronomer, sort of a token non-earthbound entity here, I suppose. But astronomy has a long history of working with computational technologies. In fact, NCSA, one of the prime reasons it was founded was to do astronomical simulations. Sort of what we do is the very large universe is filled with lots of things, and we're trying to understand those things. What is the universe made of? How old is it? To do things like that, we need a lot of help. And things have changed a lot in the last few years. It used to be that astronomy, computers, was all about simulation game. And while that's still the case, and I imagine there's a few out here today that are interested in that realm, there's other things as well. In the last, say, 10 years or so, astronomy has become a very data-rich science. There's a very, very big sky, and people like to look at it. And nowadays they're looking at it in all different kinds of wavelengths with high-resolution imagers, spectroscopy, what have you. And because of that, we're now getting to the point where understanding what our data is telling us is becoming a real problem. So a few years ago, I started realizing that this was going to be a problem, and didn't just do the standard technique, which is let's just do approximations, let's just try to find a few clever ways of speeding up our codes on existing systems. We started looking at the problem. Is the problem not our questions we're asking, but the way we're going about answering? And so that's why I'm here working with Professor Q, and we're looking at can GPUs accelerate some of the analyses that we want to do. I'm only one of the people on this campus that's actually working with GPUs. There's a number of people that are looking into this. One of them is looking at doing fluid dynamics and radiant transport in a relativistic sense, so looking at materials spinning around black holes. Can we speed up this calculation to do it in a self-consistent manner? Others are looking at data processing. Can we speed up the processing of data as it comes off the telescopes? Excuse me. We're involved here at NCSA in the Large Synoptic Survey Telescope. It's going to generate 10 to 20 terabytes of data a night, and people want to be able to look for things in that data and identify them immediately. That's a hard problem to do, given that sort of data rate. There's other projects that are being proposed that are even faster by an order of magnitude or more as far as data rates. And so being able to actually do things with that data in less than a graduate student's lifetime is an important task. I'm on the other end, I'm on the more of the data mining end, trying to take all the data after it's been processed and calibrated and trying to extract science out of that data. So two particular problems that we have looked at are very simple, very basic problems. And the idea is, can we speed these up? And fundamentally, they all come down to, we map out where galaxies are in the sky. Okay, so we have millions and millions of galaxies. We know how they're distributed. And we try to characterize what is that distribution telling us. And to do that, you actually have to measure statistical properties of that distribution. You think about it, if you just think about throwing rocks out on a road or something, you can calculate distances between pairs of rocks. That's what we do with these galaxies. We calculate distances between pairs of galaxies, which naively goes as an n-squared problem. And then galaxies calculating distances is roughly n-squared. And there's clever ways to try to speed that up, that calculation up. But fundamentally, that's what it comes down to. But of course, there's a whole hierarchy of other statistical functions that are more complex than that. You can do 3 point, 4 point, 5 point to truly understand that distribution, and then understand what is the physical processes that drove the creation and subsequent evolution of that distribution. So that's what we're after. And our initial attempts with Renmei in doing one of these simple, basic 2-point correlation functions gives us a speed of 100 on a GPU. And this was only after a student took a course, something like what you're sitting here in. And that's pretty nice for an advisor to have a student come back and say, okay, so they put up a factor of 100. Because that allows you to start thinking about, we don't just have to do what's been done in the past. We don't have to just say, well, this is what everybody else did, let's just try with more data and get another decimal point or something. We can actually start thinking about, well, what are the questions we really would like to ask? But we can't because we just don't have that computational power. And I think that's what, following along with Klaus and Batap here, the whole idea is this is an exciting time. We're here where the many core paradigm is going to change how we can go about doing science. And you're here getting on this ground floor. It's a very exciting time. And I'm very happy to be here. So now we can open up the floor and you can answer questions that you really want to talk about. I talked to you about what they want to talk about. Now, what do you want to talk about? Have any questions? Yes, Ryan.
I wonder if the panel comment, particularly in terms of that results on GPU, what's your impression of learning curve for your students or for staff to take a GPU knowledge and actually translate it to camera? Like weeks, months, years, get these kinds of results. For the actual level of
Let me direct that directly to someone who is learning Aaron. Can you answer that question? That's my student who started.
Did you get a question?
I did actually. I'm working with a group, and I started in January with zero knowledge. And from scratch, actually, right inside, we go back to really add some other members of the school. And about a semester, we were able to develop. A semester and left we were able to develop code about 17 times back. That was going from 0 to 17 times back.
In a semester?
Yeah. Well, one semester and then over the summer before we actually hit that part. So approximately one semester. That was just me.
Yeah. So actually, we have to do that in the summer. So what happens is that I have 5 students as my intern this year. One of them is a Winmate student who, of course, knows GPU programming very well already, and who are with me combining Microsoft technologies for optimizing GPU programming. At the same time, I have a biophysics student. So I pair them up. I want the biophysics student learn from this computer science student about the parallel programming concept and how GPU may help him. And he didn't end up using GPU, but they did explore together. That was just 2 weeks, and Victor made the biophysics student really feel good. I learned it. I know how GPU works, and now really go back and explore into this new area. So it doesn't take you long, but the key is to pair students up.
Actually, maybe I report from the very first CUDA class that was ever given. That was here on the campus. That was spring 2007. So the classes start here in January. And in April of the year, we submitted a 40-page paper on solving several problems with CUDA, some of them involving very large-scale CUDA calculation of charges, for example, the ribolome, got us a factor over 100. The general molecular dynamics got us a factor of about 7. And that happened between January, paper submitted towards the end of April, and published in October. So that was quite a group of people, very special people who were extremely enthusiastic, but I think the existence proved that it's possible. This spring we had a second CUDA class on campus. Both of them were given, organized by Wenbei. And again, we had 4 staff people and 4 students, and the 4 students all had to do some project. And their project was, as far as I could tell, better Wenbei. Very impressive project. They already showed some maturity, ability, and led to some real solutions that we can use in our daily work. So I would say the learning curve is from 0 to doing something, like given intelligent, motivated, and sort of capable people is just a few months.
There is another issue. If you don't have to change the algorithm, then it's much faster to get into that. But sometimes, because of the parallel architecture of the graphics processor, you have to do some changes to the algorithm, and that's, I think, both require some time because you're always thinking, why can't I do faster? Why can't I change? So you're doing simultaneously innovations in the algorithm. If you don't have to do that, and some algorithms are better suited for pattern processing, and some are not. Implicit methods are not that good for pattern processing. So that, and I think the other thing I want to say is we get a lot of benefit from that group, but we also, I think, are now fostering a link with NVIDIA, and they are doing internal software development, which we can get into that one. So I think you should just be patient, and in a year or two, the subject will become much more mature.
I would second that as well. It turns out that some algorithms, as you were just learning when I walked in, the matrix multiplication, obviously if something can leverage a CUDA gloss, for instance, and you just compile it and run it, you may get some improvement. We saw that in one of our algorithms. On the other hand, when our data rates started increasing, we had issues with data transfer and memory and things like that. And that's where, as Professor Schulten said earlier, that's where the fun begins, right? I mean, you can break down the algorithm. And so you may see a 5 or even 10-fold increase in speed by just going to GPUs and compile it. But if you spend more time, you may start tweaking and getting things. And little factors of 2 and 3 here are great because you've already had a factor of 10. And so suddenly you're at a 30, 40, 50 times speed up or something. And I saw that in our first application, which was again, students taking Linux course. Other questions? So, moving forward, ideally, what do you think the community should look like? How do people help each other out? What are the kind of things that someone like David or someone like Jan could do from industry to help people to develop these things much faster? What kind of resources or what kind of mechanism for getting some of the code, for example, NVIDIA and so on. We seem to be still struggling to actually get to the point where people can get faster development. Right? So completely, are there a couple of things that David should think about, Jan should think about on these companies to help us out?
I can say a few things that relate to CFD, computational fluid dynamics. We use a lot of linear solvers. For example, if you take a set of linear system, start from the very elementary iterative procedure like Jacobi, Baric direct solvers are not practical for simple problems, so you start Jacobi, SOR, conjugate gradients, ICT stat. There are a whole bunch of linear solvers that have been developed, and the example would be getting something like the numerical recipes, algorithms like numerical recipes on the graphics processors, and those can be used for a whole bunch of applications. But when you break down a nonlinear PDE, for example, even in electromagnetics, you break down a nonlinear PDE into a set of time-based equations, you need a linear solver. And numerical recipes is a good example. You can get that on the GPU, and you can share that, just call that up to get a set of equations.
I would totally second that. I've been saying that, in fact. And it's not so much because you want to take away fun. It's the case of going back to this first question. You can spend a long time trying different things out. And if there's a set of things that you can go in and just try out and get an idea of which is the most promising direction, that can be very valuable. because I don't want my students spending their entire graduate career optimizing their code. I want them to run it and start doing some interesting science. And so that's the concern, is that they can get sidetracked and well, I tried this, maybe this will work. And having something like numerical recipes where you can say, hey, look, go look at this chapter and talk about something along that line would be very valuable.
The NAG library is another example.
And I'll be willing to help do it. I'm not saying go do it. That may be the right way to do it, right? The whole community contributes.
Yeah.
Right.
If I could comment on that, there's on the NVIDIA website, NVIDIA.com, they're called Kudism. There are many people are posting their code, posting their case studies. There are, I believe, hundreds of applications there now. So it's a repository for. So far, I'm sure there's a lot of things that haven't been done yet, but a lot of things
In one way, one strategy that I try to employ in my group is to really make sure that the solutions that are being developed are being actually used by researchers, because many of you are probably not first programmer and then scientist, but maybe the other way around or both. You want to solve your science problems better, and that is why you want to use it. And so the same for us. So we really took advantage of the local environment where we got from NVIDIA equipment here at CFA for a cluster of GPUs. We have also several clusters from the small one to the larger one in our own group. And so what we did is we made sure that our programs that are actually soon will be released in an official CUDA version, our molecular dynamics program, that they would be running on these clusters so that the researchers would not only program and play around, but also really see the results in their daily work. And that was really a very big turnaround, because then you suddenly see that you can actually get what really works better. It's not theoretical, but it happens to you every day. And so this was for us extremely important, that we actually got the real GPU clusters working for us. And that is what actually is the case. And that is what motivates the developers and students who do the research every day to improve the code.
There's a question. Go ahead.
I would just like to comment, numerical recipes is good as a concept example, but if you encourage people to start there unless they change their software copyright practices, it's a very bad idea, because I know one particular code the government's invested hundreds of millions of dollars in that has had to spend hours and hours of time to write all of the numerical recipes examples out of their code, because the students said, hey, numerical recipes is a great solution.
Yeah.
And they commit it, and then 20 years later they have copyright violations out.
Oh, okay. I don't want to say about the copyright what code you take, but something like that, the libraries, the solvers that are numerical recipes, they have some iterated solvers, they have dense matrix solvers, sparse matrix solvers. I mean, if somebody can generate public domain solvers on the GPU that everybody else can use, I think that would be good.
You have a very valid point. And in my field, we've actually, in many projects, they explicitly state at the beginning, you cannot use numerical recipes for exactly that reason. On the other hand, it is an excellent thing for an advisor to say to a student, you're going to need to learn to do this. This book shows you how to do it. And you can actually, use their routines and everything, and then write your own or what have you. That's what I mean by when I say it's exactly the concept of here's different ways you can solve a couple of partial differential equations, as an example. Right? That's what I'm looking at. And that has to be the case, or it's going to hurt future development.
Right now, with the GPUs, it seems like a lot of the so-called easier problems that fit more easily into it are being tackled. Having on that stuff. Do you guys think that it's going to keep putting more and more problems into this, or just not them, or do you think that we're going to exhaust what we're doing and then have to use additional problems that don't fit?
Well, let me comment on.
Maybe we should keep the question. I just realized that there are more people maybe still listening. So the question is, people are jumping on working on these problems on GPU, and so are we going to quickly exhaust all the types of problems that can't be solved by the GPU, or we're going to continue to find more and more problems that can somehow be mingled or twisted or something to fit into the GPU?
So let me answer that from the viewpoint of fluid CFD, fluid dynamics. So if you go back, as I understand, my knowledge of GPU is very, very tiny. To me, it looked like the old CM1, CM2, CM5 architecture, and those were, correct me if I'm wrong, those were very well suited for things like cellular and maybe molecular dynamics. When we came into implicit solvers, you will see that there's a lot of parallel operations that you have to do, and you may not be able to map some algorithms. So you have to again develop new algorithms. But those algorithms would be slower to converge on a single processor, but maybe faster to converge on this processor. For example, Jacobi versus SOR, red flag SOR, red flag outside logic. All these things that originally maybe on a single processor are not that fast, but when you look at the parallel efficiency, it will be better on a GPU. So you would lose some performance when you start to map more complicated solvers on the GPU. The question is, would you still get a benefit for the cost that you pay? And that's it. Yes, that would be beneficial. I was going to make one more point about what the libraries of software that we may need on the GPUs, and that would be the input-output. Again, copying things to memory and trying to visualize data, that's where, again, the bottleneck will come, because you're looking at a data transfer from local memory to the global memory. And again, maybe there are some problems, but it is a parallel I.O. kind of thing. That's another point that's something improving maybe.
It's on, but I'm not on. Anyway, I'll speak loudly so it gets out and maybe eventually get picked up by the remote people. So the data transfer, I think, there certainly are issues with multiple memory spaces and the fact that you have to copy data at all, but there is a very common misconception about it being a bottleneck to copy data to the GPU. The bandwidth to and from the GPU from the core of the system is almost exactly the same as the bandwidth to and from the CPU from the core of the system. But people don't complain, oh, I have to copy the memory to the CPU. It's just a usage model that has not really gotten to the point where people are used to efficiently dealing with multiple memory spaces. And two things can happen. One is we can make people learn to get better at it, but hopefully that's not what we'll do. We also can make constructs that make it easier. And finally, we can make more and more of it transparent in hardware and hidden under the programming model.
I like to ski, and I have a wonderful analogy from skiing. It's going from skiing to snowboarding. Then it happened. Particularly older people like me were saying, this snowboarding fair, we'll get over, you can just, take easy slopes and that's it. But today you have, I think in your generation was snowboarding, then skiing. And I think it is a good analogy because first you do what is easy and what is natural. Like, for example, quantum chemistry without us realizing before is actually very, very well mapped, the GPUs. My own main computational task, molecular dynamics, is so heterogeneous that it's very difficult mapped. But we have this fight, and we have, of course, also the need. And so we are surprising ourselves almost every day that once we have the next bottleneck solved, that we are going to go further and further. We totally turn around the way we compute things in some cases and so on. And I bet I also warning to you guys, like let's say when I was at that age when I was not believing in snowboarding, we will see a lot of GPU not only as one computational means, let's say directly on a cluster dominated, right, but we will see the GPUs accelerating all our big parallel computers. So this is actually a little bit in the future, but I think it's a very realistic future that if we want to run on the best machines in the near future, we better know how to use GPU acceleration.
I have a question for the panel. So we talk about using this for speed of the code. Like when there is a point where you might also change the computational thinking, and I have no doubt that massive parallel is a feature. So I wonder, people who make people algorithms, do we have to learn about this, think the seed algorithm per se? And then give you an example. For example, physical processing, the notion of causality is ordering. So this concept of parallelism is very opposite to that. So should we also think about that by training and education and so on? And this early stage, seed algorithm, we have something working in that.
Are you talking about the barrier you've seen before you can get into production?
Let me repeat the question. I think what Ming's talking about is oftentimes you may need to rethink about the entire strategy of doing things. It may not even be a single algorithm. You may need to change the model of formulating your problem, and so that it's actually it's not sequential. Now you can do things in more parallel ways. Exactly. These things can require a lot of creativity rather than just mechanical skips, right? Which is absolutely true. In fact, this is the fundamental reason why I believe the industry is panicking at this point. Because people started to realize that in a lot of cases it's not just a straightforward transition of the same algorithm that you do a little bit tweaking and you get better results. You may need to completely rethink about these things. The fundamental model of approaching these problems, and those things can take time. And if we're not careful, it could take decades before we get there. In the meantime, what happens to the industry in the next 20 years, right? So it is a very valid question. And so why don't we let the panelists take this question a little bit? For Microsoft, what do you see?
I think that's the process of learning how to make computational thinking a natural skill. I mean, computational thinking, the term is not like you can learn having a tutorial. Let's talk about how you can be more computational thinking. It's really a practice, it's a format, and therefore, by becoming more natural in computational thinking, you design the problems from the beginning differently. I mean, this summer I learned a lot from watching my students. So 5 of them, one is from biophysics, one from biomedical. These two students think totally differently from the other 3 students who are, compiler, core computing students. So when my biophysics student says, I have a embarrassingly parallel problem, that's why I'm here this summer. And then we analyze these problems, we realize this is really sequential. But he has his reason to call it parallel because he's doing the same thing over and over again to which he could do the same thing at the same time. That's what he meant. But however, there's a dependency from this and to there, so therefore computer science called it sequential. And then when he talked about optimization, he meant zero parameter classic mathematics problems. So you have many equations and you make them each side all zero. That's what he meant optimization. At first, Victor was trying to say, oh, physics is a great tool for optimization, but that's a different thing. So it's the mindsets that needs to take some change before you can reach that performance stage. And I think that's what you were talking about. It really takes some practice, and we may say it may take years, but let's just start with something concrete. Parallel computing, GPU concept. It's more important of learning the concept than GPU itself. Who knows? A few years later, maybe something replaces GPU. But it's important to get into the right thinking process.
How about the panelists? From your experience, how big a change of thinking that you see your students go through, in order to make a real difference?
Yeah. So in my group, programming is pretty much a team sport. So we have a wonderful team, and it's maybe like football, and you have some people on the benches and some people on the field. And in the past, there were more like maybe the macho types on the field who knew solutions, who went through them many, many times. And today we have more ladies, for example, very interesting, and we have also more the mathematical, soft-spoken types on the field. So really, I saw a shift of who are the key players who participate there, and I really consider myself extremely fortunate that for some reason, I don't know, I had really more mathematical-oriented people waiting on the benches, ready to actually join the team. So it is a new game. It is more intellectual. That's what I call the fun part. And so I don't know, it might be more difficult for one person who has to do all by herself or himself to change the mind. But if you are thinking a bit more broadly, you're looking right and left, and you're working with a few more people, then actually you can do this very quickly, and you will definitely enjoy the new dimensions that are posed by programming for GPUs.
From the fluids part, I would just simply say that the problems we are tackling now are so large. If you're doing a direct numerical simulation of or even another approach for larger simulations, the single processor times are so large that people are not interested to wait that long. In fact, they would go for another approach that is much more empirical rather than go this fundamental approach. So the only way you can interest industry to really go for the more sophisticated approaches is to give them cheap computing. And the cheap computing now would come not from single processors, but by many processors. So parallel computing is there, has been there since 95, something like that. And one has to just simply think about using those, whether it's simple domain decomposition, which is probably very easy to understand, or much more intrinsic massive parallelism like on simple machines or graphic process. So I think it's going to be a new paradigm for everyone in CNC.
Well, let me go back to I think what the points you were making. When one of my students was working on a particular problem, the first thing was you do a simple thing and you see a speed up, and this sort of led into, well, what if I try this, what if I try that, and this often came as Klaus was saying, you talk with others, others who know more about GPUs or about the problem or different approaches, and sometimes you go back to the actual underlying math or physics that's sitting in the problem, and can you rearrange the equation, can you solve it some other way, and that's what we ended up doing. We came up with a checklist of different things we could try, different ways of attacking the problem, and sometimes, maybe most of the time, something that as the older generation would say, something that our intuition was telling us is not a fruitful way to solve the problem actually turned out to be a fruitful way, and so it does sort of teach you, if you're open to it, to think differently and to open your mind to other possibilities, which is, as I said, it's a fun part of trying things out.
One comment I'll reply to, I don't know who was said over there, we don't even know if it'll be GPUs. It won't be GPUs as we know them now, but hopefully it will be GPUs of the future. They will change too. But the biggest task, I think, in learning new ways of programming is to change your thinking about what's expensive and what is cheap. And it has to do, for GPUs, at least in their current implementation, it has to do with this embarrassing amount of processing ability that there is. So often the most, not the most efficient, but the fastest GPU algorithm is one that is relatively wasteful of computation, because recomputing something is 20 times cheaper than reading from data in memory. So often the seemingly overly brute force dumb way to do it is the fastest way. And you've done some gratuitous floating point, but it's 10 times faster. That's true for sorting. It's true for a lot of searching and scanning operations. Doing extra work is the cheaper way. So there'll be, for the next generation, there'll be different new things we have to learn as architectures change.
Okay, so we may have time for one question, but if we don't see any questions, let's thank the panelists and also continue the discussion. Most of the panelists will be around for the reception, so we can continue some of the conversation. Okay.